So we've gone over the evidence that the basal ganglia, thalamus and basal forebrain are the behavior selection subsystem predicted by the theoretical considerations. Let's now have a more detailed look at the information processes performed by these subcortical structures and how they're implemented. Remember, this is the overall architecture. Earlier we discussed how brain anatomy and physiology seem to indicate that the basal ganglia select the behavior recommended most strongly by current cortical receptive field detections. And now we're going to have a look at the information model for how the basal ganglia does this in a bit more detail. So this is the major connectivity of the basal ganglia as we've looked at it before. Now, earlier in the course, we identified this list of the information functions that have to be performed by a behavior selection subsystem. Getting receptive field detections from the cortex, assigning recommendation weights, making sure that just one behavior is selected, adjusting recommendation weights in response to reward feedback, and so on. What I'm going to do is to go through each of these in turn and look at how the basal ganglia implements each function. The striatum gets massive input from the cortex. And of course, each cortical input is a receptive field detection. And it's interpreted by the striatum as a set of recommendations in favor of lots of different behaviors. In the striatum, individual spiny projection neurons correspond with different behaviors. Each spiny neuron gets one or two inputs from a large number of different cortical neurons. And because each input is isolated on a spine, its input weight can be adjusted independently. So each input synaptic weight corresponds with the strength of the recommendation by the corresponding receptive field detection in favor of the behavior corresponding with the striatal neuron. So the degree of output from the spiny neuron is the total recommendation strength in favor of that behavior. The determination of the most strongly recommended behavior overall is performed between the direct and the indirect paths. In the GPI-SNR, neurons also correspond with behaviors. The GPI-SNR neurons fire tonically all the time, so they're constantly inhibiting their corresponding behavior. A selected behavior is implemented by a drop in the inhibition of the thalamus by the corresponding GPI-SNR neurons, which allows release of a set of cortical outputs to an appropriate target. The D1 and D2 populations of projection neurons in the striatum both calculate total recommendation weights in favor of one behavior, but the information meaning of their outputs is slightly different. The output of a D1 neuron can be viewed as a recommendation in favor of a behavior. The output of a D2 neuron can be viewed as a recommendation against any behavior except one. The D1 neurons directly inhibit the GPI-SNR neurons corresponding with their behavior, and therefore encourage implementation of that behavior. Via the indirect path, the D2 neurons excite the GPI-SNR neurons corresponding with every behavior except their own, and therefore discourage implementation of all those other behaviors. So effectively, there's a competition to determine the most strongly recommended behavior. That selected behavior is then implemented by a decrease in the inhibition of the thalamus. And that releases appropriate cortical outputs to their targets. Now, it's important to try to avoid implementing two incompatible behaviors at the same time, like trying to move the same arm in two different directions. On the other hand, it's also important to avoid the situation in which no behavior is ever selected. If activity in the direct path is too strong, you might get multiple behaviors. If activity in the indirect path is too strong, you might not get any behavior at all. So there has to be a balance between the two paths. This balance is maintained by the dopamine loop back to the striatum from the SNC. Tonic firing of SNC neurons maintains a background level of dopamine in the striatum. This background dopamine inhibits the D2 neurons and very slightly excites the D1 neurons. If there's too much activity in the GPI-SNR, this indicates that no behavior is being selected. There's too much inhibition of the thalamus, and no cortical activity is being released. In this situation, inputs from the GPI-SNR increase the proportion of SNC dopaminergic neurons firing in the tonic mode, increasing the level of background dopamine in the striatum, and therefore inhibiting the D2 neurons and reducing activity in the indirect path. This reduces the excitatory input to the GPI-SNR, reducing its activity and increasing the chance of a behavior being selected. Now, in novel circumstances, there may be fewer strong recommendation weights because of the lack of sufficiently similar past experience and the consequence feedback during that experience. However, it's nevertheless sometimes important to try something in order to learn the best behaviors in those circumstances. So there's a tendency towards exploratory and experimental behaviors in novel situations. This tendency is implemented by input to the striatum from the hippocampus. Remember that in carrying out its primary change management role, hippocampal activity correlates with the degree of novelty in an experience. So this activity can also be used as an input to the striatum to recommend increasing the probability of a behavior selection. Increasing the probability of behavior selection is itself to be regarded as a behavior that's recommended by the hippocampal inputs to striatal neurons corresponding with that behavior. If sufficiently recommended, these striatal neurons could implement the behavior by inhibiting interneurons in the SNC that themselves inhibit tonal output by the dopaminergic neurons. And that would result in more background dopamine, more inhibition of the D2 population, and a higher chance of some behavior being selected. Consequence feedback following a behavior must often adjust the recommendation weights that generated the behavior. Part of this process again uses the dopaminergic projection from the SNC to the striatum. But in this case, uses a projection from the striatum to the SNC. Looking more closely at this projection, in addition to the D1 and D2 populations in the striatum, there's another population that I talked about earlier that targets the SNC. This additional population is located in structures in the striatum called striosomes, while the D1 and D2 populations are located in the matrosomes. The two types of structure, as I mentioned earlier, are physically separated but interwoven with each other. Striatal neurons in the striosomes get inputs from the cortex that it interprets as recommendations in favor of reward behaviors, and if enough input weight is present, they fire. That firing triggers burst firing of dopamine neurons in the SNC, which acts back on the striatum to change the weights of recently active striatal neurons. So in information terms, the recommendation weights that resulted in the recent behavior are increased. If the same behavior has often been rewarded in the same circumstances in the past, the burst dopamine firing is suppressed so that recommendation weights don't increase excessively. Striatal neurons correspond with different specific behaviors, and a cortical neuron can only have recommendation strength in favor of the behavior if it synapses onto the corresponding striatal neuron. Now, cortical receptive fields are defined heuristically, and the brain doesn't know in advance exactly which receptor fields are most appropriate for recommending a particular behavior. But there are lots of cortical neurons that target the striatum, and it will be very expensive in connectivity and processing resources to have every cortical neuron target every striatal neuron. Hence, there have to be mechanisms for selecting the most useful cortical inputs to each behavior. One approach is a general genetically defined mechanism. Receptor fields of a particular complexity will on average be more effective for recommending particular types of behavior. Hence, there's a tendency for cortical areas to most strongly target a limited range of striatal regions, as we described a little earlier. However, there's still a need to limit the inputs to individual striatal neurons from those areas, and in some cases, an input from a receptor field in a different area might still be valuable. So, the issue is how to identify the best cortical neurons to synapse onto each striatal neuron. Now, you recall that there was a similar issue in the definition process for receptive fields. And an important way to improve the probability of selecting the more appropriate connections between cortical neurons utilizes the sleep process. In the same way, during sleep, a partial rerun of recent experience leads to provisional connectivity between cortical and striatal neurons that are often active at the same time. And correlated activity suggests a higher probability that the connection could be behaviorally useful. But of course, the provisional synapse could disappear if it's not rewarded within some limited subsequent period of waking experience. And as expected from this model, sleep deprivation makes learning of skills less effective. We've identified more than one role for the dopamine link between the SNC and the striatum. One is ensuring that one and only one behavior is selected. The other is regulation of changes to recommendation weights in various ways. Let's have a look at how this occurs on a more detailed level. Dopamine neurons, as I talked about earlier, fire in two modes: a constant tonic firing at about 4 Hz and a burst firing mode which generates a group of spikes at about 20 Hz. A significant proportion of the dopamine released at striatal synapses as a result of tonic firing diffuses into the environment and creates a background concentration of dopamine that I've represented by the purple dots. It's this background dopamine that regulates the balance between the direct and the indirect paths. And the level of concentration is determined by the proportion of the dopamine neurons that are firing in the tonic mode. Appropriate inputs can trigger burst firing of dopamine neurons, but this burst firing has a relatively small effect on the background dopamine. The reason for this is the burst firing inputs also activate molecules in the synaptic cleft that recycle the dopamine, and a relatively small proportion escapes into the environment around the neurons. But burst firing tends to result in a relatively long-term increase in the weights of recently active synapses onto recently active striatal neurons. In other words, it increases the recommendation weights of recently detected cortical receptor fields in favor of the recently selected behavior. And this can help us understand those observations of dopamine activity in the brains of monkeys when they are carrying out tasks and getting rewards that we discussed earlier. The monkey first sees an image that indicates that a specific task will need to be performed in the near future. Shortly afterwards, the monkey hears a tone indicating the moment when the task should be carried out. If the task is carried out correctly, the monkey gets a reward, like a piece of fruit. The activity of dopamine neurons in the monkey's brain were directly recorded when all this was going on. When a new task was being learned, there was a burst of dopamine firing at the time of the reward. So receptive fields detected within the presence of the reward were recommending firing of striatal neurons that triggered dopamine burst firing, increasing the recommendation weights in favor of the way the monkey had performed the new task. But once the task had been learned, the dopamine burst firing coincided with the trigger stimulus. Now, how can we understand this? Well, there's no recent monkey behavior to be rewarded, but the burst firing could lead to a bit of dopamine leaking into the environment around the striatal neurons. And an increase in the background dopamine increases the chance of a behavior being selected. So what is happening is that the tone is indicating that if a behavior is initiated in the near future, a reward following that behavior is likely. So it's behaviorally valuable to increase the chance of a behavior being selected. But if the reward isn't provided, there's a dip in the tonic firing, and therefore a dip in the background dopamine. And this kind of dip reduces recently active synaptic weights. So it will reduce the chance of the behavior being selected in the future in similar circumstances. At the neuron level, the implementation of the regulation of dopamine neuron firing is actually quite a bit more complex than I've described, involving additional structures, interneurons, and different types of neurotransmitter receptors. But we don't need to get into that at this point. At the chemical level, we've already described how dopamine can trigger long-term synaptic weight increases in the cortex, and the mechanisms are similar in the striatum. However, there are some complications because negative consequence feedback, like the absence of an expected reward in the monkey task that we talked about earlier, must actively reduce recommendation strengths. And as we saw, a dip in tonic dopamine firing appears to be the trigger for the required synaptic weight decreases. And it appears that if D1 and D2 receptors are activated simultaneously in the striatum, the result is long-term synaptic weight decreases, while activation of just D1 receptors leads to long-term synaptic weight increases. However, these receptors may be on different neurons. One different type is the excitatory cholinergic neurons in the striatum, which are known to play a role in long-term synaptic weight changes on the striatal projection neurons. But again, I won't get into any more detail on this. Instead, we'll go on to consider the issue of strategic, tactical, and detailed rewards. Brains need rewards to change behavior recommendation weights, but behaviors can be on different levels of complexity. And even though the implementation of a strategic behavior is generally lots of detailed behaviors, a strategic reward isn't entirely appropriate for rewarding every individual detailed behavior. And the example I've used more than once is the musician who's rewarded by applause at the end of a concert. The reward is appropriate for the strategic behavior of choosing to play a concert at that place and time, but it's much less appropriate for rewarding every individual muscle movement and every mental process that led up to those muscle movements, because some muscle movements could have been better than average and some worse than others. So if I summarize, if the brain detects receptive fields within, say, applause at the end of a concert, those receptive fields are appropriate for recommending increases to the synaptic weights corresponding with the strategic decision to give the concert. But they're less appropriate for rewarding the behaviors of selecting each of the pieces of music performed. Some may have gone less well than others, and even less appropriate for indiscriminately rewarding all the individual muscle movements, some of which might have been in error. So the brain needs other receptive fields that are appropriate for recommending more tactical and detailed rewards. And also the brain has to give those receptive fields recommendation strengths in favor of the appropriate reward behaviors. So the problem is how to identify those receptive fields. In other words, how to assign recommendation strengths in favor of reward behaviors to the right receptive fields. For example, when learning to play, a musician gets comments from a teacher, and receptive field detections within those comments can be used by the brain to recommend reward behaviors, even rewards of relatively detailed behaviors. But a teacher can only go so far, and the musician's brain needs to progress far beyond the teacher's instructions and feedback. So suppose that a teacher has helped create in the musician's brain some initial recommendation weights to reward more detailed behaviors. How can those recommendation weights be enhanced? The key to further improvement is to recognize that a strategic reward can not only reward a strategic behavior, but can also reward the reward behaviors that rewarded all the tactical behaviors used to achieve the strategic behavior. So, applause at the end of the concert can also reward the reward behaviors that rewarded the tactical behaviors like selecting the pieces of music. So, whatever receptive field detections recommended rewarding tactical behaviors can have their recommendation strengths in favor of such rewards increased by the strategic reward behavior. And similarly, tactical rewards, like applause at the end of one piece of music, can reward the behaviors that rewarded more specific behaviors like major body movements, and so on. So, how does the brain implement this reward management? Well, different cortical areas detect receptive fields that are most appropriate for recommending different types of behavior. The orbital and medial prefrontal areas are more effective for recommending strategic behaviors. The dorsolateral prefrontal for recommending more tactical, the premotor for recommending general motor movements, and the motor cortex for recommending detailed motor movements. But remember, this isn't completely clear-cut. One area may have some effectiveness for recommending multiple types of behavior. The striatum is where receptive field detections are interpreted as behavioral recommendations. The most ventral part of the striatum, the shell of the nucleus accumbens, selects the most strategic behaviors, assigning recommendation weights in favor of such behaviors to receptive field detections derived heavily from the orbital and medial prefrontal cortex. And in fact, the cortex-like amygdala also projects to this region, providing receptive field detections that recommend general types of behavior, including rewards. The somewhat less ventral core of the nucleus accumbens selects more tactical behaviors, assigning recommendation strengths in favor of such behaviors, mainly to receptive field detections in the dorsolateral prefrontal cortex, but also using receptive field detections in the orbital and medial prefrontal and perhaps other areas. The central striatum selects more specific behaviors on the basis of recommendations by the premotor cortex, and again uses some receptive field detections by the dorsolateral prefrontal. And the most detailed muscle movements are selected by the most dorsal part of the striatum, using receptive field detections by the motor cortex, but also some from the premotor cortex. Most behaviors are actually implemented by release of cortical receptive field detections to drive detections in other areas. So, selection of a strategic behavior is implemented by release of the receptive field detections that recommended the behavior to other areas that will detect receptive fields appropriate for recommending tactical behaviors that are consistent with the selected strategic behavior. But reward behaviors are implemented by the striatum driving activity in the midbrain dopamine neurons. And the more ventral part of the striatum tends to target the more ventral part of the midbrain dopamine neurons, often called the ventral tegmental area, while the more dorsal parts of the striatum target the more dorsal parts of the midbrain dopamine neurons, where, of course, they're called the SMC. The reward behaviors generated in the midbrain dopamine neurons then act back on the striatum to change synaptic weights. And again, as I used earlier in the course, to reduce the degree of overlap in this drawing, I've illustrated the striatum twice. Once on the left, sending outputs to the midbrain dopamine neurons, and on the right, getting inputs back. And there's a spiral pattern to this connectivity that implements the hierarchy of reward management. And I described this spiral pattern a little earlier. The strategic reward behaviors accepted by the shell are implemented back into the shell, but also into part of the core. So the strategic rewards are rewarding both the strategic behaviors and also the behaviors of rewarding tactical behaviors. The tactical reward behaviors accepted by the core are implemented back into the core and part of the central striatum. The specific reward behaviors accepted by the central striatum are implemented back into the central striatum, but also into part of the dorsolateral striatum. And the dorsolateral striatum also rewards the dorsolateral striatum, but perhaps a bit more dorsal area of it. So this spiral of connectivity implements the process by which strategic reward behaviors reward both strategic behaviors and more tactical reward behaviors, and so on.